Okay, so in this video I'm going to have a look at another proof by induction, and it's a proof by induction of this particular series here. It's just another example. So we'll run through this particular problem here. We've got to prove that this is equal to the left hand side is equal to the right hand side here. Now on the left hand side here we can see that this is a series and it goes from 1 up to n. So it'll look like this. If we put 1 in here, for example, we'll get 1 squared plus 1, which is 2, times 1 factorial, so the first term will just simply be 2. The second term then will be 2 squared, which is 4 plus 1 is 5, and 5 times 2 factorial, which is just 2, that will give us 10. And so on, that will just go on forever. You can put 3 in here, you get 9 plus 1 is 10, and 10 times 6 will be 60. In other words, 3 factorial is just 3 times 2 times 1, which is 6. So that's your 3 factorial there. So and so on. This goes on forever anyway, and that goes all the way up to that will go up to sort of n squared plus 1 times n factorial. That's on the left hand side, and we want to show that that's equal to n times n plus 1 factorial. This is the right hand side here. Okay, so we have a series on the left hand side and we want to show that it's equivalent to this kind of formula here on the right. So let's start. Usually what we do is we look at the first number here, which is 1. We put 1 into the left hand side and 1 into the right hand side and see do we get the same. So let's have a look. We call this the proposition. This is a proposition that this is equal to this. So we want to look at P1 first, the proposition that it's true for P1. So let's look at that. So we're going to look at the left hand side first. The left hand side will give us 1 squared plus 1 times 1 factorial. So 1 squared plus 1, that's 2. 2 times 1, which will give us 2. And we've done that already here. We've seen that the first term here is 2. So let's look at the right hand side. The right hand side then, same thing again. You just put in 1 on the right hand side, so you get 1 times 1 plus 1 factorial. And that will give you 1 plus 1 is 2. 2 factorial is 2. That's just 2 times 1. And that's 2 times 1 here, which just gives us 2. So the left hand side is equal to the right hand side. Therefore P1 is true. It works for n is equal to 1. Okay, so let's get into the main bulk of this this proof now. So what we're going to do next is assume the proposition is true for n is equal to k. So some number that we're going to call it k, and we're going to assume that it is true for n is equal to k. So what we're going to do is just put k in here. In other words, if you look at this series here, I've just written it out a different way here. So we're going to write it out like this. So you're going to assume that this is true. So this is your assumption here. So I'll do that in a different color actually. Let's do it in this color here. This is your assumption here, okay? So your assumption then is that 2 plus 10 plus 60 all the way up to k squared plus 1 times k factorial is equal to k times k plus 1 factorial. So this is our assumption. We are assuming that this is true. And what we want to prove then is that it's true for the next term up, which is k plus 1. So we want to prove the following. So we want to prove that 2 plus 10 plus and so on all the way up to, again, k squared plus 1 times k factorial plus, now remember we're going up to k plus 1 now, so each of these we replace with k plus 1. So we're going to go with k plus 1 squared plus 1, that's this bit. Instead of k, we put in k plus 1. And this bit here will just turn into k plus 1 factorial. We want to prove that that's equal to, this becomes k plus 1, and this here becomes k plus 1 plus 1, which is just k plus 2 factorial. Okay, so this is what we want to prove. We are assuming that this is true, and if this is true, then we want to prove that this here is true. So now what we're going to do then is just look at this particular equation here. And what we're going to do in particular, we're going to look at the left-hand side. And we're going to see if we can turn the left-hand side into the right-hand side. If we can show the left-hand side is equal to the right-hand side, then pk plus 1 is true. And we'll go from there then later on. So let's have a look. What we're going to do first is we're just going to look at this part of the series here. Just this part of the series here. Now if you look at that, you'll see that this here is this here. Okay, and we know we've assumed that all of this is equal to this part here. So instead of this here, we can write this, or in other words, instead of this part of our series here and the bit we want to prove, we can just write the right hand side up here. So that's what I'm going to do. So let's do that. We've got k times k plus 1 factorial, that's this bit here, plus k plus 1 squared plus 1 times k plus 1 factorial. We want to show that that's equal to k plus 1 times k plus 2 factorial. Okay, so let's do that then. So we got to turn this into this here if we can. Let's see then. Well, the first thing I'm going to do is I'm going to square this bit out here and add the 1 and see what we end up with. So let's see, we end up with k times k plus 1 factorial here, that's just this bit here, plus, now if I square this and add this 1, I'll get k squared plus 2k plus 1, which is plus 2, times k plus 1 factorial. We want to show that that's equal to k plus 1 times k plus 2 factorial. Okay. So let's see, what have we got here? Now, if you look at this term here and this big term here, we've got a k plus 1 factorial here, we've got a k plus 1 factorial here. So what I'm going to do is factorize the left-hand side using a common factor of k plus 1 factorial. So in other words, I'm going to take this k plus 1 factorial, and I'm just going to divide this by it and this by it. I'm going to take it out of these two terms here. So in other words, I'll get k here. In other words, if you multiply this by k, you'll get this here. Plus, take it out of this here as well, and you'll end up with k squared plus 2k plus 2. And again, we're just showing that that's equal to k plus 1 times k plus 2 factorial. Okay, so now all I've done is factorize this left-hand side. I've taken k plus 1 factorial out of these two terms here. Now, so let's continue on with this and see where it leads us. We have k plus 1 here, and here we end up with, this is k plus 1 factorial here, so we end up with k squared plus, we have 2k here plus k, that will give us 3k plus 2 is equal to this. I won't keep writing this down, but you get the idea. Now, on the left-hand side here, we end up with k plus 1 factorial. This is a quadratic trinomial here, so we can just simply factorize that, and we end up with k times k, 2 times 1 plus times plus, and that will give us k plus 1 factorial times k plus 2 times k plus 1. Now, if you just think about what a factorial means, and factorial really just means that, say for example, if you have 3 factorial, that's just 3 times 2 times 1. Now, if you have 4 times 3 factorial, if you think about what that means, 3 factorial is 3 times 2 times 1. If you multiply 3 factorial by 4, that's just the same as writing 4 times 3 times 2 times 1. That's really just 4 factorial. Okay, so we're going to do something similar here with our left-hand side. So if you look at this, you've got a k plus 1 factorial times k plus 2 factorial. But that's just simply k plus 2 factorial. K plus 1 factorial is k plus 1 times k minus 1 and so on. K plus 2 times this is just k plus 2 factorial times k plus 1. If you look at our right hand side here, we've also got a k plus 1 times k plus 2 factorial. So this is equal to this, so we've proven that the proposition for k plus 1 is true. So this is true if pk is true. So if pk is true, then we've proven that pk plus 1 will be true. Okay, so we're almost there now at this stage. Right, so we just have to write the last bit in then. Now we know then that P1 is true. We've proven that at the very beginning. We put 1 into the left-hand side, 1 into the right-hand side, and they were equal. So the proposition for when k is 1 is true. And we know that pk plus 1 is true if pk is true. Therefore, by induction, Pn is true for all n is an element of n. So whenever you have a natural number, the proposition will be true. So in other words, if we take k as 1, we know that k plus 1 will be true. In other words, the proposition, if the proposition is true for 1, and we've just proven that it will also be true for 1 plus 1, which is 2. So we know that P1 is true. Now we know that P2 is true. But if P2 is true, by induction, P3 must be true as well, and so on. P4 will be true, and so on, all the way up. Okay, and that's it.